Welcome to This Explainer. Okay, picture this. You're walking downtown, looking up at a massive skyscraper, or maybe you're driving across a sprawling suspension bridge, and you just stop and wonder, how is this whole thing actually staying up? I mean, when you really think about the sheer mass of modern buildings, literally thousands of tons of steel, concrete, and glass suspended hundreds of feet in the air, the stakes of a structural failure are almost unimaginable. We tend to think of these structures as solid, completely unmoving blocks, but the truth is there are unseen, microscopic physical laws governing every single beam and cable around us. Today, we're going to explore exactly how engineers use the science of elasticity to prevent structural failures in the modern buildings we rely on every single day. Let's dive into it. So think about a towering skyscraper on an incredibly windy day. You've probably heard that they actually sway. It sounds absolutely terrifying, right? But ask yourself, why do skyscrapers sway in the wind but not just completely collapse? Here's the thing. If these giant structures were perfectly rigid, they would literally snap under the immense pressure of a storm or the sudden rumbling of an earthquake. The secret to their survival isn't absolute stiffness. Actually, it's the exact opposite. To really get this, we need to look at two fundamental concepts, elasticity versus plasticity. When we talk about elasticity, just think of a rubber band. You stretch it, and it snaps right back to its exact original shape. This reversible shape change is the absolute hallmark of a safe building. Plasticity, on the other hand, is like pushing your thumb into a piece of clay. You make a dent, and the change is permanent. In engineering, plastic deformation means irreversible, incredibly dangerous structural damage.
Which brings us to a crucial realization. Elasticity, not just rigid strength, is the true secret to modern architecture. It's calculated flexibility that allows our buildings to survive everyday stresses. A building literally has to be able to bend, stretch slightly, and then bounce right back to its original form, exactly like that rubber band. But how does solid steel act like a stretchy rubber band?
Here is our roadmap for today's explainer. We're going to cover 1. The atomic scale, 2. Hooke's law and stiffness, 3. The stress-strain journey, 4. Engineering safe buildings, and finally, 5. The future of materials. Let's start with Section 1, the atomic scale, zooming into the invisible forces. First up, we have to talk about restoring force. The formal definition is the internal resistance generated by atomic bonds to return to their stable equilibrium configuration after being displaced. But what this actually means is that when a force pushes or pulls a solid object, the atoms inside are shoved out of their comfortable, stable positions. Atoms strongly prefer this equilibrium state, mostly because it represents their lowest possible energy level. So when they're pushed out of alignment, the interatomic bonds immediately resist the movement. They desperately want to go back to normal, and that generates a force that pushes back against the deformation. There is such a great way to picture this. Quote, "When you stand on a steel plate, you do not break the springs," meaning the atomic bonds. You compress them slightly and they push back. I love that. Imagine solid steel not as this immovable block, but as a dense, microscopic network of incredibly stiff mattress springs. You step on it, the springs compress microscopically, and they push back with an equal force. That is exactly what elasticity looks like in action. Moving right along to Section 2, Hooke's law and stiffness, the mathematics of the spring. Okay, this is actually pretty wild. Back in the 17th century, the English scientist Robert Hooke published this bizarre jumble of text, CEIIINOSSSSTTUV. Hooke had actually discovered the mathematical secret of elasticity, but to protect his intellectual property while he was still refining his watch springs, he published his law as a secret Latin anagram. 2 years later, he finally revealed the decrypted answer, U tensio sic vis, which translates to as the extension, so the force. Hooke's decreted law is beautifully simple. It's F equals negative kx. The restoring force is linearly proportional to the displacement. In plain English, if you stretch an elastic object twice as far, it simply pulls back with twice the force. The negative sign there just means the force pulls in the opposite direction of the stretch. It's elegantly simple, but it describes the restoring force in almost everything elastic right up until the point it breaks. Now, obviously not all materials are equally springy. Engineers measure this exact stiffness as Young's modulus. A higher number basically means the material is much, much harder to stretch. Just notice the massive, quantifiable difference between stiff steel, way up at 200 gigapascals, and soft lead down at just 16. This metric tells a structural engineer exactly how a material is going to behave under a load. It's totally vital information.
For example, if you're building a skyscraper's core weight-bearing columns, you need a material with a high Young's modulus, like steel, to ensure it doesn't compress too much under thousands of tons. Meanwhile, a lower modulus material might be perfectly fine for some decorative, non-structural element. Let's move to Section 3, the stress-strain journey, a material's life and death. Let's walk through this stress-strain curve step by step. Imagine engineers pulling a material apart just to see what happens. First, up to the proportional limit, the material perfectly obeys Hooke's law. Step 2 is the elastic limit. That's the absolute maximum stress before you get permanent damage. Cross that, and we hit Step 3, the terrifying yield point. This transition is absolutely critical. Internally, the atomic bounds are being stretched so far that they actually start to slip past each other and break their original connections. This is exactly where that plastic permanent deformation begins. Step 4 is ultimate strength, which is the absolute maximum load it can take. And finally, Step 5, fracture. The material physically breaks. As an engineer, you want to stay very, very far away from Step 5, and ideally, you never even cross Step 2. Which brings us to Section 4, engineering safe buildings. Applying the science. So to guarantee we never cross that dangerous threshold, engineers use what's called a safety factor. Usually, it's a massive buffer of 2 to 4 times the expected load. Engineers don't just build a bridge to withstand the expected weight of everyday cars. They design it to handle multiple times that weight. This buffer guarantees that the materials never, ever leave that safe, temporary elastic region we just talked about. Even in the face of completely unpredictable elements, like a sudden 100-mile-per-hour wind gust or a bumper-to-bumper traffic jam of semi-trucks, they ensure those microscopic atomic springs are never stretched past their breaking point. So the crucial takeaway here is how this applies in the real world. Relying on precise elastic limits gives us the suspension systems in our cars that compress to absorb road impacts and immediately expand right back. It gives us bridge cables that can stretch and flex slightly under heavy winds or traffic, dynamically distributing the load, and then return to their exact shape without permanent, catastrophic plastic deformation. It allows massive steel building beams to bow slightly under the weight of a heavy, snowy roof without bowing permanently. It even allows seismometers to detect the tiny, elastic ground motions of earthquakes. Calculating this exact elastic limit is quite literally what keeps our critical infrastructure standing firm. And finally, let's look ahead to Section 5, the future of materials, defying traditional limits. Okay, this is where things get genuinely mind-bending: auxetic metamaterials. Normally, when you pull a rubber band, it gets thinner in the middle, right? Well, auxetic materials do the exact opposite. They actually expand when you pull them. They achieve this by using really unique geometric architectures, things like reentrant honeycomb structures, rotating rigid units, or periodic origami folds. Think about how certain origami patterns unfold. As you pull the ends, the folded ridges open up, causing the entire structure to widen in all directions simultaneously. By doing this, they can absorb absolutely incredible amounts of energy, offering amazing fracture toughness for things like aerospace components and advanced protective equipment. Which leaves us with this final, truly provocative thought. Could origami folds and expanding auxetics make tomorrow's buildings entirely indestructible? I mean, just imagine a future where our structures don't just rigidly resist extreme forces, but gracefully adapt, expand, and absorb them, never even coming close to that fracture point. It totally changes how we think about the very cities we live in. Thank you so much for joining me on this explainer. Until next time, keep looking for the hidden science all around you.